Hi, my name is Ian Fogarty. I'd like to talk to you about alkanes today.
When talking about alkanes, they end in A and E. So whenever you see an ending of A and E, it's going to tell you some things. It's going to tell you, one, that there are carbon-carbon single bonds, that it follows the formula CnH2n plus 2. The bonds can rotate, which is an interesting thing. We haven't talked about that much yet. That there are 109.5 degree bond angles and they're tetrahedral, and the hybridization is sp3. We'll talk more about what hybridization is later. We have prefixes to designate how many carbons each thing has. So if it's got one carbon, it's going to get metha, and two carbons gets etha, and three carbons gets propra, buta, penta, hexa, hepta, octa, nona, deca. Students often use septa in here for 7, and that's for something else, or ena in here for 9. It's not organic chemistry. Organic chemistry is hepta and nona. So a couple of quick examples might be something like this. 1, 2, 3, 4, 5, 6, 7. So this would be heptane, or my line diagram looks something like that. Or maybe 1, 2, 3, 4. Should be butane. So the buta tells me there's 4 carbons. The ane tells me that they're all carbon single bonds. These bonds can rotate right around here or right around there. That'll come important in the next slide. And they have bond angles of 109.5, and they're tetrahedral. So here we have a 1, 2, 3, 4, 5, 6, 7, 8 carbon chain, heptane. We've shown it just in a straight line here. It should be the zigzag for 109.5 degrees. But it turns out for this that bonds can rotate. And so if this bond right here were to rotate, you would end up with a line that looks something like that. So we still have the same number of carbons in a row, it's just that it can go around corners. So we shouldn't let the fact that it goes a little bend in it bother us a whole lot. It also turns out that more than one bond could rotate, and so you could end up with something like this. And so these molecules are all identical in every way. It's just that their bonds are spinning, and their bonds are spinning all the time. We also shouldn't worry about left to right or up and down. So this straight chain right here is exactly the same as this straight chain. When they're in a bottle somewhere being shook around, there's going to be molecules in all orientations. And so this is the same or that is the same. So we can go left to right, up, down, and around corners when we want to start counting things. So these are all examples of octane, which you have in your car. And so here is C5H12. We've got each carbon has 2 hydrogens, plus each end has extra hydrogen. It turns out we can have branches. Branches use the ending, the suffix YL. And so we could do and build some other thing. So let's build something else. This also has C5. If I look quickly, here's my CH3, that's good, and my CH2, my CH3, but it looks like there's a problem here, that this only has 1 hydrogen attached to it. And so will my pattern be continued? Will this follow the rule C5H12? So far so good, so far so good. Looks like there's a problem, then that one seems okay. It looks as though this might not be a good thing. What we haven't done yet is completed this carbon. This carbon doesn't have all its bonds yet. So when I put those hydrogens in, it is true that this carbon is short 1 hydrogen. However, it is also true that this carbon has an extra one. So there are 3 carbons that have 3 hydrogens. So the hydrogen that used to be attached here is now down here. So the formula, even though there's a straight chain or there's branches, still works C5H12. So now I'd like to look at something called isomers and numbering our carbons. So here we have heptane. So 1, 2, 3, 4, 5, 6, 7, 7 carbons. That's going to be C7H16. And we would simply number them. Carbon number 1, 2, 3, 4, 5, 6, 7. However, we could also make some branches. So we could take this carbon right here, break it off of carbon number 6, move it over 1, and attach it down here. And so we would end up with something like this, where here is our parent chain, 1, 2, 3, 4, 5, 6, and then we have a 1 carbon branch. So here is my parent chain, and there's my 1 carbon branch. So this is going to be called 2-methylhexane. We have our parent chain, 1 carbon, 2 carbon, 3 carbon, 4 carbon, 5 carbon. So there's our parent chain, and then we have our branch off of carbon number 2. Well, we could also have something like this, where again we have our hexane, but instead of the branch being off here, it's just moved over 1, and so there's our 1 carbon branch. So it gets the methyl, the Y for the branch, and the meth for the 1 carbon, and we have the hexane for 6 carbons, and then a parent chain. They're all single bonds, and they can all rotate. This would be carbon number 1, 2, 3, 4, 5, and 6. Well, that's great. And if we follow this process, we can end up with something here, 1, 2, 3, 4, 5, 6. So 4-methylhexane, and 1, 2, 3, 4, 5, 6. 5-methylhexane. And at first glance, this all looks great and dandy. There's a problem with this, though. And the problem with this is molecules don't know that in North America we will read from left to right. They don't understand that. They're just in a bottle and they're all moving around. And so we have to be able to think that maybe these are going to be spun upside down, they're going to be moving around. What happens to this if we just simply look at it in the opposite direction? If we just flip this left to right, and we just flip this left to right, and we can also flip it up and down, turns out that this is really just that spun around. And so there is no 4-methylhexane. 4-methylhexane is the same as 3-methylhexane, and there's no sense in having 2 different names for the same molecule. They don't know, the molecules don't know that they're supposed to line up in a certain way. And so it's up to us as humans to figure out that 4-methylhexane, 4-methylhexane, and 3-methylhexane are the same thing. So this is not a good number. We would prefer smaller numbers if possible. So 3-methyl is better than 4-methyl. And likewise, when I look at this one, this is also the same as that. And so there's no such thing as 5-methylhexane. It's really just 2-methylhexane. When I do my counting, I'm going to want to make sure, let's get rid of those. When I do my counting, I'm going to want to make sure that I give the branches the smallest possible number. So instead of going this way, 1, 2, 3, 4, 5, 6, I really ought to be going this way, 1, 2, 3, 4, 5, and 6. And so I would end up with 2-methylhexane instead. That's the proper number. Over here, the same, 1, 2, 3, 4, 5, 6, and this would be the same as 3-methylhexane.